talking about quantum mechanics might sound like a modern and technical subject, but as physicist Brian Cox explains, its roots go back to a much older human pursuit, the desire to understand the patterns that govern nature. Brian Cox takes us to the year 1610, when Johannes Kepler, best known for his laws of planetary motion, wrote a small book titled On the Six-Cornered Snowflake. According to Kepler, while crossing the Charles Bridge in Prague during a snowfall, he stopped to observe the snowflakes landing on his coat. Each one was different, yet they all shared a six-pointed structure, a symmetry that made him pause and reflect. Kepler wondered why nature repeated this form so precisely. He suspected there must be a deeper cause, an invisible structure underlying that symmetry. Today, we know he was right. The shape of a snowflake is determined by the water molecule, H2O, which forms a distinctive angle between the oxygen atom and its two hydrogen atoms. Although Kepler had no concept of molecules, in his book he wrote that he was knocking on the doors of chemistry, a thought far ahead of his time. Brian Cox highlights this moment as an early glimpse into the quantum world. Visible forms, like a snowflake, are shaped by invisible laws that govern matter, an everyday example that connects us to a far deeper reality. It's remarkable to think that a simple snowflake, fleeting and delicate, could hold within its symmetry a key to unlocking the secrets of matter. Kepler's intuition echoes through centuries of science, leading us deeper into the quantum world. Fast forward to the late 19th century, when scientists faced a new mystery. Why do atoms emit light in specific colors? Brian Cox points to a familiar example, the old sodium vapor street lamps, glowing with that characteristic orange hue. But why that color specifically? The answer began to take shape thanks to Max Planck, who in 1900 proposed a revolutionary idea. He suggested that light is not emitted continuously, but rather in tiny packets of energy, which we now call photons. At the time, Planck believed it was merely a mathematical trick to make the equations match experimental results. But his idea turned out to be a profound insight into how the universe really works. Planck introduced what is now known as Planck's constant, symbolized by the letter H, and formulated a fundamental equation. Energy, represented by E equals H, multiplied by the frequency of the light, represented by F. In other words, E equals H times F. In this formula, E is the amount of energy carried by each photon, F is the frequency of the light, and H is the universal constant that now bears Planck's name. This simple yet powerful relation marked the official birth of quantum mechanics. Brian Cox concludes that this was the moment when physics began to see the universe not as something continuous and predictable, but as a structure made of energetic building blocks. This journey, from Kepler's snowflakes to Planck's photons, reminds us that behind every pattern lies a question, and behind every answer, a new mystery unfolds. Although Max Planck proposed in 1900 that light is emitted in small packets of energy, what we now call photons, he himself was not convinced that these packets were real. As physicist Brian Cox explains, Planck considered the idea more of a mathematical tool, a convenient way to describe the behavior of matter without necessarily assuming that light was truly made up of discrete particles. He did not believe that light, as we know it, behaved as a stream of individual entities. But in 1905, Albert Einstein took a much bolder step. In the very same year he revolutionized physics with his special theory of relativity, he also published a paper on an experimental phenomenon known as the photoelectric effect, a work that would later earn him the Nobel Prize. The photoelectric effect is easy to describe, yet profoundly puzzling. When you shine light on a metal surface, sometimes electrons are ejected from the material. However, what's strange is that no matter how intense the light is, if the frequency is too low, no electrons are emitted. For example, you can shine a very bright red light, but if its frequency isn't high enough, nothing happens. In contrast, even a dim blue light will cause electrons to be released. This behavior didn't make sense. If light was simply a wave carrying energy, one would expect a brighter light, regardless of color, to eventually dislodge electrons. But reality didn't behave that way. Einstein proposed a radical idea, that light behaves as if it's made up of individual photons, each carrying a specific amount of energy. If a photon doesn't have enough energy to knock an electron free, no amount of photons will help. But a single photon with sufficient energy will eject an electron immediately. The key, Einstein explained, is that a photon's energy is directly proportional to its frequency. Using the formula E equals h times f, where E is the energy, h is Planck's constant, and f is the frequency, Einstein resolved the mystery. Einstein's insight not only confirmed Planck's idea, it transformed it. It told us that light isn't just a wave nor merely a mathematical convenience. It is something deeper, stranger, a dual entity, a paradox in motion, revealing that reality can behave in ways we never imagined. Brian Cox emphasizes that this marked a turning point in science. For the first time, the quantum nature of light was seen not just in how it was emitted, but as a fundamental property of light itself. This wasn't just a scientific discovery, it was a philosophical shock. It meant that nature, at its most fundamental level, does not follow the rules we intuitively expect. Instead, it dances to a rhythm both precise and profoundly mysterious. Yet many scientists of the time resisted this shift. Even Planck, years later, wrote that Einstein's belief in photons should not be held against him. Evidence of how revolutionary and uncomfortable the idea still was. Brian Cox reminds us that the real challenge of quantum mechanics isn't the mathematics, it's the concepts themselves. Ideas so counterintuitive, they still stretch our understanding of reality to this day. As Brian Cox explains, one of the great challenges of modern physics is that quantum mechanics fundamentally defies our intuition and the very foundations of classical physics that have guided us since Newton. For decades, quantum mechanics was taught following its historical development, beginning with the photoelectric effect, then moving on to atomic structure, and finally the models proposed by Ernest Rutherford and Niels Bohr. Bohr suggested that electrons within an atom do not orbit freely like planets around the Sun. Instead, they can only occupy certain positions or energy levels, which we now call orbitals. This idea was revolutionary. In classical physics, moving charged particles such as electrons should constantly emit energy and eventually spiral into the nucleus, making atoms inherently unstable. Yet, atoms are remarkably stable. Bohr's solution was to propose that electrons exist only in specific, well-defined energy states, and they do not emit energy while they remain in those states. Though practical, this explanation remains strange and counterintuitive. Today, as Brian Cox notes, many educators prefer to teach quantum mechanics based on what we now understand, accepting that this is simply how the universe behaves, no matter how bizarre it may seem. One of the clearest ways to illustrate this difference is through the concept of quantum superposition. Imagine flipping a coin. In classical physics, the coin can land on heads or tails, one or the other, never both. However, in the quantum world, as Brian Cox describes, a particle can exist in a mixture of states. It's as though the coin could be 30% heads and 70% tails at the same time, or any other combination. These kinds of objects are called qubits, and they form the foundation of emerging technologies like quantum computing. And this isn't just theoretical. Superposition and quantum probability are being harnessed in real technologies. Quantum encryption, teleportation, and sensing are becoming tangible realities. These aren't futuristic dreams. They're early steps into a new understanding of nature that challenges everything we thought we knew about cause and effect. A real-world example is the spin of an electron, which can be up or down, but can also exist in a superposition of both states. This is where the true break with classical physics occurs. In everyday life, we use probability to express our ignorance. For example, we might say there's a 50% chance of rain tomorrow, because we lack enough information to make a precise prediction. But in quantum mechanics, as Brian Cox clarifies, these probabilities don't reflect ignorance. They are fundamental properties of nature. At the quantum level, reality is probabilistic by definition. This unsettling idea lies at the heart of quantum mechanics and is what has fueled decades of debate and deep challenges to our understanding of the universe. Among all the experiments ever devised by physics to challenge our understanding of reality, Brian Cox highlights one that, in his words, captures the very essence of quantum mystery: the Double Slit Experiment. This experiment is so powerful that the physicist Richard Feynman, one of the greatest minds of the 20th century, once said that it contains the only mystery of quantum mechanics. In fact, in his famous lectures on physics, freely available online, Feynman dedicates the first chapters to its explanation, recommending it as the best entry point into the quantum world. From its very inception, the Double Slit Experiment has served not only as an academic curiosity, but also as a conceptual cornerstone for every physicist exploring quantum phenomena. Since the 1960s, figures like Feynman have used this experiment to push students to think beyond classical limits. It has inspired thousands of studies, simulations, and even philosophical inquiries aimed at answering the ultimate question: what is a particle, really? Imagine the following setup. You have a cannon firing electrons, those tiny particles that make up atoms. In front of the cannon stands a barrier with two narrow slits. Beyond the barrier is a screen that registers the impact points of the electrons, like a canvas capturing their marks. If electrons were simple particles, tiny bullets, we would expect them to go through one slit or the other, forming two clusters on the screen behind each slit. But that's not what happens. Instead, a pattern of alternating bright and dark fringes appears, much like what you'd expect from water waves passing through both slits. This pattern is called an interference pattern, and it is a clear signature of wave-like behavior. What's even more baffling is that the same pattern emerges even if you fire the electrons one at a time. There is no way for a single electron to interfere with another, yet the wave pattern builds up regardless. How can that be? Brian Cox explains that the most widely accepted interpretation today is that each electron explores all possible paths simultaneously, passing through both slits at once. This might seem absurd, but the experiment repeatedly confirms this behavior. To understand this, we turn to Feynman's mathematical description. Every possible path an electron can take even the most bizarre ones, like a trip to the Andromeda Galaxy and back, is represented by a complex number, a mathematical value with both a direction and a magnitude. Feynman compared these numbers to the hands of tiny clocks, rotating with time. The recipe is simple, yet profound. For any given point on the screen, you sum up all the clock hands corresponding to all possible paths. If many clock hands point in the same direction, they reinforce each other, making that spot likely. If they point in opposite directions, they cancel out, reducing the likelihood of the electron appearing there. The result is the interference pattern we observe experimentally. At this point, the question is not how to calculate the result. We know how. The question is, what does it mean? According to Brian Cox, quantum mechanics gives us the correct predictions, but it leaves the deeper philosophical question unanswered. Is the electron really taking every possible path? Or is this just a clever mathematical trick? Many physicists argued that yes, the electron truly does explore all possible paths simultaneously. It's a claim that challenges our deepest assumptions, that particles travel one path, like marbles down a chute. But it aligns with the observations. Here's a thought-provoking twist. What if this behavior isn't limited to the quantum world? Brian Cox emphasizes that there aren't different rules for the subatomic realm and the world we see. The same principles that govern electrons apply to every atom in your body. The reason we don't observe these effects in daily life is because they get averaged out when dealing with large numbers of particles. What makes this all the more fascinating is that these quantum rules don't stop at electrons or photons. The same strange behavior can, in principle, be observed in larger molecules, and even in systems made up of thousands of atoms, though it becomes technically challenging. This raises profound questions about where, if anywhere, the boundary lies between quantum behavior and classical reality. But that's beginning to change. Today, quantum technologies, such as quantum computers, are no longer speculative. They're real and advancing rapidly. Superpositions, interference patterns, and probability amplitudes are being harnessed to perform computations that no classical computer could manage within the age of the universe. This isn't just theory, it's happening now. Quantum sensors, for example, are being developed to measure magnetic and electric fields with unprecedented precision. Quantum cryptography promises unbreakable communication, and quantum materials are being engineered to revolutionize everything from energy storage to digital processing. It's a technological revolution powered by quantum mechanics. Brian Cox concludes with a powerful reflection. This strange wave-like behavior of matter is not optional. It is how the universe works. Whether we like it or not, whether we fully understand it or not, quantum mechanics governs reality. And as our tools improve, as we build machines that depend on these principles, we're not just glimpsing the quantum world, we're beginning to live in it. Just like Kepler once stared at snowflakes and suspected hidden patterns beneath, today we stare into the quantum realm and realize we are only beginning to unlock its secrets. Throughout the 20th century, the debate surrounding quantum mechanics often seemed philosophical, detached from the practical world. But as physicist Brian Cox explains, these ideas are now becoming tangible technologies, especially with the rise of quantum computers. Unlike traditional computers, which rely on bits that can be either 0 or 1, quantum computers use qubits, units that can exist in superpositions representing multiple states simultaneously. This principle, as Brian Cox reminds us, is rooted in everything we've explored in previous chapters. Particles that can exist in several states at once. The key to quantum power lies in entanglement, a deep connection between qubits such that whatever happens to one instantly affects the other, regardless of distance. Brian Cox uses the example of two entangled electrons. If one is on Pluto and the other on Earth, measuring one instantly determines the state of the other. This phenomenon unsettled Einstein, but today it is a verified and essential property of nature. What's truly fascinating is how these properties scale. With 2 qubits, there are 4 possible combinations. With 3, 8, and so on. With 100 qubits, the number of possible configurations is 2 raised to the power of 100, a figure that surpasses the number of atoms in the observable universe. Brian Cox explains that companies like Google, IBM, and Microsoft are already building these systems. They could solve problems that are impossible for classical computers, from complex chemical simulations to large-scale optimization tasks. These breakthroughs are not theoretical dreams. They're being tested in labs, developed by engineers, and supported by governments worldwide. The momentum is accelerating, and what once took decades of scientific speculation is now unfolding in real time before our eyes. But Cox also cautions that the true value of quantum mechanics goes beyond technology. It's revealing a reality far deeper and stranger than we ever imagined. What once seemed a theoretical curiosity has now become a tool capable of transforming the world. Brian Cox also reminds us that this isn't just about what we can build, it's about what we can become. By understanding and applying these laws, we're reshaping the boundary between knowledge and mystery. Each discovery is not just a triumph of science, but an invitation to reimagine reality itself, and to question whether consciousness plays a deeper role than we dare admit. Each step into this quantum frontier reveals not only new data or technological capacity, but confronts us with a much more unsettling truth. Reality is not what we thought it was. From the snowflakes that inspired Kepler to the mysterious light that intrigued Planck and Einstein, everything has led us to this moment, a realm where particles explore all paths simultaneously, where information transcends distance, and where certainty dissolves into probabilities not as errors, but as the very fabric of the universe. What's perhaps most disquieting, as Brian Cox warns, is that these strange rules aren't confined to the microscopic world. They're here now, functioning in every atom of your body, every ray of light entering your eyes, every moment you experience. Quantum physics teaches us that we live in a universe where the impossible is simply what we do not yet understand, where every choice, every observation, every moment is part of a cosmic web of infinite possibilities. Perhaps the most provocative idea of all is that in building technologies based on these principles, like quantum computers, we are not merely creating new tools. We are knocking on the same doors that Kepler, Planck, and Einstein once approached centuries ago. And as we cross those thresholds, we cannot help but wonder, how much more is left to uncover? What ultimately is reality? Brian Cox leaves us with a certainty and a challenge. The universe still holds its secrets, and perhaps, just perhaps, the greatest experiment of all is our own consciousness trying to understand them. And that concludes our video. If you enjoyed the content as much as we did, don't forget to subscribe so you don't miss a single episode. Leave a comment below. We'd love to hear your feedback and suggestions for future videos. And don't forget to turn on notifications to stay up to date with all our updates. Thanks for being part of our community. See you in the next video.